This is a video from section 11.1. A sequence A sub n is increasing if A sub n is less than A sub n plus 1 for n greater than or equal to 1. A sequence A sub n is decreasing if A sub n is greater than A sub n plus 1 for n greater than or equal to 1. And we'll look at an example of an increasing sequence and a decreasing sequence shortly. Now, a sequence is monotonic if it is either increasing or it is decreasing. Now, let's look at an example of an increasing sequence. So for here, you can let A sub n equal n squared. All right? Now, I want you to notice, let n equal 1. And so A sub 1 is 1 squared equals 1. A sub 2 is 2 squared, which equals 4. A sub 3 is 3 squared, which equals 9. So you notice how, as the index goes up, the corresponding values of the sequence are also going up. So you notice that? We have 1, 4. These are the terms of the sequence. 9. The next one would be 16, I claim. 25. And we go on and on and on. So this is an increasing sequence. Now, let's take a look at an example of a decreasing sequence. So for this one, I'm going to let A sub n equal, we'll just do 1 over n. Now, if I replace n with 1, I get 1. If I replace n with 2, I get a half. I replace n with 3, I get a third. So you notice as the index goes up, the corresponding values of the sequence are going down, right? So the sequence looks like this. We start with 1, then we go to a half, then a third, then a fourth, and on and on and on. And so that's a decreasing sequence. Okay, now I want to give you another definition. A sequence A sub n is bounded above if there exists a number m such that A sub n is less than or equal to capital M for all n greater than or equal to 1. A sequence A sub n is bounded below if there exists a number that we'll call small m. such that little m is less than or equal to a sub n for all n greater than or equal to capital 1. Now, so notice how we have bounded above and bounded below, and I'll do an example of each. Now, if a sequence a sub n is bounded above and below then a sub n is what we call a bounded sequence. So a bounded sequence has to be bounded from above and bounded from below. And I want to take you back to this example. So I'm going to let a sub n equal n squared. Okay? Now, I want you to notice something. 1 is less than or equal to n squared for n greater than or equal to 1. That is true, right? And so what we can say is that the sequence a sub n is bounded below by 1. Okay? We just need one number that works. There could be others. So I can claim that this sequence is also bounded below by a half. That is a fact. But we just need one number that will work the whole time. Okay? Now, one thing I want you to note, this sequence a sub n is not bounded above. Okay? It's not bounded above because it's just going to keep going and going and going and going and going. When I let n go to infinity, a sub n is going off to infinity. So it's not bounded from above. Now, let's go back to number 2. If I have a sub n equals 1 over n, right? Now, I want you to look at the terms of the sequence. We have 1, a half, a third, a fourth, a fifth, and it keeps going and going and going. So notice, if I take 1 over n, this is less than or equal to 1 for n greater than or equal to 1. Also, 1 over n is greater than or equal to 0. We'll use 0 for n greater than or equal to 1 as well. So I want you to notice something. This sequence is bounded above by 1 and below by 0. Okay, so this sequence, a sub n, is bounded. Again, it's bounded above by 1, below by 0. We're a bounded sequence. Now, there's a very important theorem, okay? And it says the following. It says every bounded, monotonic, which means either increasing or decreasing. Monotonic sequence must converge. It doesn't tell me what the sequence converges to. We just know that it has to converge to something. That's important. We don't know what it converges to. So I want to stress that. Now, I want to take a look at an example. So let's take a look at a sub n, which is equal to 1 over 2n plus 3. Okay? Now, is the sequence a sub n increasing, decreasing, or not monotonic? Okay, now, if you want to know the quickest way to do this, this is what I would do. We're going to look at the corresponding function. So we're going to let f of x equal 1 over 2x plus 3. And primarily, we're going to focus on the interval 1 to infinity. Because when you look at the sequence, we only care about what happens when n is 1, 2, 3, etc. Okay? That's all we care about. Now, can we agree that this is equal to 2x plus 3 to the negative 1? Take the derivative. When I take the derivative, I get negative 1 times 2x plus 3 to the negative 2 times 2. But that's negative 2 over 2x plus 3 squared. Now, let's notice something. Negative 2 over 2x plus 3 to the second is less than 0, strictly less than 0, on 1 to infinity, immediately. And so what that tells me is that f is decreasing. This is from Calculus 1, on 1 to infinity. And because that function is decreasing on 1 to infinity, what that tells me is that a sub n is greater than a sub n plus 1 for n greater than or equal to 1. If the function is increasing, essentially the discrete function will also decrease. And so what that tells me also is that a sub n is a decreasing sequence. Now, that's a decreasing sequence. And so remember, a sub n is 1 over 2n plus 3. And so therefore, a sub n is bounded above by 1/3, or excuse me, let n be 1, so 2 times 1 is 2, 2 plus 3 is 5. So it's bounded above by 1/5. We could have said 1/3, by the way, for the record. A sub n most certainly is bounded below by 0 because none of the terms are negative, right? And so what does that say? That says this sequence is bounded. And therefore, this sequence converges. Now, we happen to know that this sequence converges to 0, but knowing that the sequence is monotonic, and in our case, we proved it's decreasing and bounded, we showed that the sequence converged. And that's how we do a problem like that. Let's take a look at this example. We'll do one more example for this video. What if I give you a sub n is equal to 3 minus 2n e to the negative n? Okay. Now, I'm going to write this as 3 minus 2n over e to the n. Now, what I'm going to do is I'm going to let f of x equal 3 minus 2x over e to the x on, and again, our focus is on 1 to infinity. All right? Now, let's take the derivative. Derivative is nice to do this. And let's again remind ourselves. F of x is 3 minus 2x over e to the x. So we're going to do the quotient rule. So the derivative of a constant is 0, but so we're focused on that second term, right? So I'm going to take e to the x bottom times the derivative of the top, which is negative 2, minus negative 2x times the derivative of the bottom, which is e to the x, and I'm going to divide by e to the x squared. So this is negative 2 e to the x plus 2x e to the x divided by e to the x squared. I'm not calling it e to the 2x just yet. Okay. Now, let's factor out a 2e to the x. And when I do that, I get negative 1 plus x, I believe, right? And then I'm dividing by e to the x squared. Now, here I can write 2 times x minus 1 divided by e to the x, right? Because here, that e to the x cancels one of these. Now, watch carefully. I claim 2 times x minus 1 over e to the x is greater than 0 for x bigger than 1. So what does that say? Okay. That says f is increasing when x is bigger than 1. So it's an increasing function when x is strictly bigger than 1. What does that say? That says a sub n is less than a sub n plus 1, right? And that's going to be for n bigger than or equal to 2. And that's okay. And so that says a sub n is an increasing sequence. It doesn't always have to start at 1, okay? Now, here's the question, right? It increases. So this sequence is bounded below by the first term of the sequence. So we can say this is bounded below by 3 minus 2 times, and I could just plug in 2 times 2e to the negative 2, which is 3 minus 4 over e squared. And we could probably make this a little easier. I'll give you a different idea. Now, here, I want to show you something. If we plug in a1, we get 3 minus 2 times 1 e to the negative 1, right? Which is 3 minus 2 over e. And that's positive. Because remember, e is approximately, it's pretty close to 3. It's not exactly 3, right? Of course. It's 2.71828, right? But we're almost at 3. And so 3 minus 2 over e is positive. If I plug in a2, I get 3 minus 2 times 2 e to the negative 2, which is 3 minus 4 over e squared. And that's also positive, for sure. And so what we can say is this sequence is bounded below by 0. Most definitely. And the sequence just keeps getting bigger and bigger and bigger. And so a sub n is bounded above, we can say by, now notice, if we put in a sub 3, we get 3 minus 2 times 3 e to the negative 3, which is 3 minus 6 over e to the third, right? So we're taking 3 and subtracting something positive. So this can get no bigger than 4. So we'll go back here and say that this sequence is bounded above by 4. And so, therefore, we can say that this sequence, a sub n, is a bounded sequence. And by that theorem, we can say that this sequence a sub n converges. Does that make sense? I wanted to go back, and I thought it was easier to show you that that sequence is bounded below by 0. That's an easier sell. So, okay, that'll conclude this video for section 11.1, and we talked about bounded monotonic sequences.